This is calculus class. We study limits of a sequence. Previous video, I introduced definition of a sequence, definition of limit of a sequence. There is just so many ways to find the limit of a sequence. I wanna give some methodologies to find limit of a sequence, this slides. First method is end behavior of function. So function, we learned a lot of different function in college algebra, pre-calculus. We know the end behavior of functions. To use end behavior of function, we also find the limit of sequence. So first theorem they give to you, x approaches infinity, fx gonna be approach to L, then Fn is represented sequence, only whole number. Then same thing is An, limit of An go to L, same behavior they're gonna show. So this case, you're gonna use the graph and see the end behavior. That's the best way, you guys, thinking about this limit, guys. The first one is, let's talking about this limit. So first one is A1 limit and approaches infinity 1/8. So I'm thinking of function f of x, 1/x function, because x is gonna be here, any real number. I just plug in the n whole number, that's gonna be 1n. So if you know the end behavior 1/x natural function, I'm gonna sketch here. This one, always positive way. So x approaches infinity, go to this direction. This function approaches this horizontal line. That's gonna be 0. So this limit is going to 0. Okay, so and the behavior give the limit of sequence too, guys. Okay, let's go to B. Limit n approach to infinity e to the n equal where? So fx gonna be function e to the x function, right? So you're gonna sketch this function right here, guys. E to the x exponential function looks like that. So x approach to infinity. What kind of behavior for x? That's going to infinity. The same thing is the sequence going to infinity. That's you find the limit of sequence too. So third one is gonna be, guys, look at this graph. Everyone remember this graph of exponential function? So let's go to this one. C gonna be right here, guys. C gonna be right here. Limit n approach to infinity, e to the negative n. So fx gonna be, you see fx gonna be e to the negative x graph. Everyone remember the e to the negative x graph? This looks like this direction, right? So what kind of end behavior this? X approach to this. This end behavior approach horizontal line equals 0. So this sequence going to 0. Okay? Last one, this one, ln function, guys. ln function, d right there, limit n approach to infinity ln n. So I'm gonna sketch ln n function. This is ln x function. This is fx, ln x. So x approach to infinity. This ln function go to infinity, increasing. So this limit also infinity. That's one way you find the limit of a sequence. When you see the sequence, you can figure out what kind of function they represent, and you're going to sketch the graph, or you remember the end behavior, then easily find the limit of that sequence. Second methodology, we're going to find the limit of a sequence. We use L'Hopital rule. We learned the L'Hopital rule previous module. So we're going to use L'Hopital rule here. So when do you use L'Hopital rule, guys? 0 over 0, infinity over infinity. In this case, we're going to use, guys, right here. You're going to use infinity over infinity. That's, we're going to use L'Hopital rule. One part is go to negative infinity is fine. So infinity over infinity form of sequence. So then you're going to use L'Hopital rule, take a derivative each sequence. So take a derivative with respect n, take a derivative with respect to n f prime of n, g prime n. So that's we're gonna use L'Hopital rule to find the limit of this sequence. Okay, guys, keep in mind that when you're using L'Hopital rule, you have to dispose infinity over infinity. Okay, or it can be positive or negative, positive or negative. It doesn't matter, but always it should be infinity over infinity. You're gonna use L'Hopital rule. Let's do this example right here, guys. Look at this one. This one is four different sequence right here, guys. So let's just start to find the first one, you and I. So here is A. I say I'm gonna use L'Hopital rule, but we have to check it out. We have to check it out. This one is gonna be, guys. Look at this. So denominator also going to infinity. So this is infinity over infinity. We can use L'Hopital rule. So limit n approach to infinity. Derivative n with respect to n, that's gonna be 1. Derivative n plus 1 is 1. So this limit of sequence is 1. So you can apply the L'Hopital rule here when they have infinity over infinity. Second part of this one is right there, guys, limit n approach to infinity ln n over n. ln n. Previous example, we say ln n going to infinity, right? That's going to infinity. N approach to infinity, which meaning is n numbers that each term give the n is increasing, a n also increasing, go to infinity. Of course, n go to increasing. So infinity over infinity, we can use L'Hopital rule and approach to infinity. Find the derivative ln n is 1 over n. Find the derivative n is 1. This is limit and approach to infinity 1 over n. We're talking about this one, and approach to infinity 1 over n going to 0, guys. Okay, that you find this limit of sequence. Let's practice more complicated one. Let's go to this one is, let's go to here. So this one, let's try to this one. This one gonna be, and this term is, guys, look at this one going to infinity. This one going to infinity. Because numerates dominate. So this case, guys, what you have to do, infinity minus infinity, you cannot use L'Hopital rule. Guys, remember the previous module? So you have to make infinity over infinity. So I'm gonna put that together, guys. Same denominator. Okay, so then let's just simplify. N square n and q plus 4n square. Here is very careful. Here is negative, negative. So negative n q minus n square. So bottom is n square plus 5n plus 4. That's you simplify. Then let's see this limit. This one is cancel out. So limit gonna be 4n square minus n square, 3n square, n square plus 5n plus 4. Now, look at this form. Top is numerator going to infinity. Denominator going to also infinity because n square is dominating term. So you can use L'Hopital rule. 3n square, derivative of 3n square is 6n. Derivative n square is 2n. Plus derivative 5n is 5. Still, this is infinity over infinity. We're going to use L'Hopital rule one more time. 6 over 2. That's limit going to be 3. So if you want to use the L'Hopital rule, always make. How to make it? infinity over infinity. Okay, let's go to the last one, guys. The last one is here. E to the n. We did the previous one, right? This going to infinity and go to infinity, right? So we can use L'Hopital rule there. Derivative e to the n, derivative n is 1. So limit n approach the infinity, e to the n is going to infinity. That's you find the limit of each sequence. If you want to use the L'Hopital rule, you have to indeterminate form infinity over infinity. Next method I want to introduce is squeeze theorem for sequence. This is a little tricky part, but guys, I'm going to introduce squeeze theorem here, then give the one example how gonna use squeeze theorem, okay? Also, this example is very important. Squeeze theorem is gonna be say it's like squeeze theorem for limit in the calculus 1 class. We wanna find the limit of Bn. Here's key idea. Bn is right here. But we know the limit of An, limit of Cn, both are same limit L. Guys, get the idea? We know the limit of An, limit of Cn, but we don't know the limit of Bn. But limit of An, limit of Cn is the same L. Then squeeze theorem say Bn, limit of Bn is also L. So look at this one. I sketch here. An is right there, Cn is right there. That's going to some one value is L. But middle, between the two sequences in the middle of Bn, should be going to the same number, go across the same number. That's the squeeze theorem say. So let's practice this theorem by this important sequence, guys. Anyone remember m factorial meaning is? So I'm going to write down m factorial is 1 factorial is 1, 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3. That's the meaning of factorial. So 1 over n factorial is, here is 1 over 1 factorial is 1. 1 over 2 factorial is 1 times 1 times 2. 1 over 3 factorial means 1 over 1 times 2 times 3. So this sequence going to where? Guys, look at this denominator. The number is getting is bigger and goes on, definitely going to 0. Then how gonna prove it, guys? How gonna prove it? I'm gonna prove it, guys. Look at this one using squeeze theorem, very simple way. But this limit is very important. So if you now remember how to prove it, but you have remember this limit of 1 over n factorial going to 0. Okay, let's prove it. This one is, I'm gonna using squeeze theorem is, I wanna prove this way, guys. M factorial, I'm gonna introduce right here, guys. I'm gonna erase this whole thing, need more space right here. So M factorial meaning, is 1 times 2 times 3 all the way n. Guys, make sense? Of course, this one is greater than n, right? Obviously. So I'm gonna flip it, recycle, okay? Reciprocal, I'm sorry, not recycle. So I'm gonna put 1 over n. Here is 1 over n factorial. Which one is bigger, guys? Definitely 1 over n is bigger because n factorial bigger than n. Of course, 1 over n factorial is greater than 0, right? So let's take a limit. So squeeze theorem say limit n approach to infinity 1 over n factorial, limit n approach to infinity 1 over n, limit n approach to infinity 0. 0 is no matter what, always go to 0. It doesn't matter n go to infinity. So this term is, first term is 0, second term is 0, third term is 0. So this is going to 0. We prove it 1 over n. That's the limit going to 0. So this one should be what? This going to 0, this going to 0. Middle term should be go to 0. That's how to prove limit and approach to infinity, 1 over n factorial, 1 over n factorial sequence going to 0, very fast going to 0, guys, okay? So from here, guys, one important sequence I'm gonna give idea is kn, 2n over n factorial, 3n over n factorial, 4n over n factorial, all this sequence going to 0 because the factorial is very fast increase, increasing so fast. So this limit goes to 0, guys, okay? Let's another way to use this squeeze theorem for sequence, guys. So look at this one. Limit and approach to infinity sine n over n. So you have time to use L'Hopital rule, right? But an approach to infinity, sine n not going to infinity, n go to infinity, sine n doesn't. So we cannot use L'Hopital rule. L'Hopital rule is out. So how are we gonna find the limit of this sequence? I'm gonna using squeeze theorem because guys, sine is gonna be maximum is 1, minimum is -1. Okay, so that's the here. So sine n is no matter what n value, sine value gonna be maximum always 1, minimum is always -1. So here we're gonna divide the n both sides, guys. So -1 over n sine n over n. Here is 1 over n. So we want to looking for what, guys? This limit. But we know the limit of this sequence. We know the limit of this sequence. So limit of -1 over n, negative, we're going to take it out the sign, 1 over n, 0, right? Also, limit 1 over n is 0. This one 0, this one 0 is the same middle part. Limit and approach to infinity. Sine n over n should be 0. That's the squeeze theorem say. Okay, so we can find the sequence. The limit of sequence is going to same limit. Then we're gonna limit of middle sequence going to have the same limit. Okay, let's go second one. Same thing here. Cosine n. We cannot use L'Hopital rule, guys. Make sure this one is -1 and 1. So we're gonna add 1 plus cosine n, 2 and 0, divide by n. 0 over n is 0, right? 0 over n is 0, guys. What is the limit of 2 over n? 0. Limit of 0? 0, 0, 0, 0 going to 0. So limit of n approach to infinity, 1 plus cosine n, and of course they go to 0. That's a squeeze theorem say. Okay, guys? Next methodology is another important theorem to find the limit of sequence, okay? Limit of sequence is L. This sequence is going to the function, inside the function. Then function is continuous. We're gonna put this limit sign inside the function. Find this limit and evaluate the function. That's gonna be limit of this sequence. Guys, make sense? So here is the thing. We know the limit of sequence first, then find this limit of sequence, guys. That's we're gonna do it, okay? Here is a very important example right here, guys. Look at this one. So look at this cosine pi over n. We know the limit of pi over n. Also, cosine is continuous function. So how can find this limit? So we want to find limit of pi over n first. So we're going to find the pi over limit of pi over n. Then we're going to plug in that limit in the function. So let's find this one first, guys. Limit of n approaches to infinity pi over n. The pi is constant outside the limit of n approaches to infinity 1 over n. 1 over n is 0. Pi times 0 is 0. So this limit going to be 0. Cosine 0 is, that's going to be 1. That's you're going to find the limit of sequence first, and then you put that limit in the function. Okay, that's you're going to do it. How about second one? Second one is a little thing before you find here. So before you find the limit of this one, first thinking about property of log, okay? This is limit ln. Here is negative. Property of log say you're going to have change into the one log condensate. That's going to be division, right? Then what are you going to do next? Ln function also continuous function. So we put the limit inside. How can find this limit? This time we're going to using L'Hopital rule, infinity over infinity, right? So 1 over 1. So this limit is 1, ln 1, ln 1 gonna be 0. This example say two things. At first, when you see log, you put together, condense the log, and then you using this theorem to find this limit. Next one is we're gonna discuss limit of geometric sequence. Geometric sequence is very popular sequence. Also depends on ratio, common ratio. The geometric sequence might be convergent, might be divergent. So you have very careful with common ratio, guys. See the here, for example, is gonna be R is common ratio. R is greater than 1. Let's say R is 2, guys. So I'm going to give example of here. R is 2. So I have geometric sequence going to be 2n. Then n is each term. What happened to each term? First term is 2. Second term is 2 square. Third term is 2 cube. Fourth term is 2 first. It's going to be increasing. So R is greater than 1. That's going to be infinity. Guys, make sense? This is divergent. Okay? Second is article 1. Article 1 is each time. Article 1 is, okay? So first term is, it doesn't matter which is the first term. Let's first term is 1. Second term is 1. Third term is 1. Fourth term is 1. So that is always stay the same. So this one is convergent. So R is between the 0 and 1. I'm gonna talking about negative 1 and 0. R is between 0 and 1. So let's say R is 1.5. So first term is 1, second is 1.5, third term is 1/4, fourth term is 1 over 8. What happened? This one going to 0. So this one is converge and going to 0. Guys, make sense? I'm gonna highlight this one. That's gonna be converge, limit gonna be 0. Let's go into negative part. Negative meaning is gonna be, let's say, article negative 1 and 0. I'm gonna give the ratio gonna be negative 1.5. Okay, guys, negative 1.5. So I'm gonna give first term gonna be, guys, first term gonna be negative A1 is negative 1.5. A2 gonna be u times negative 1.5, 1/4. Alternating sign, right? A3 gonna be negative 1 over 8. That's alternating, but they close to 0. So also this one going to 0. Okay? R is greater than negative 1. Then what happened? So that's negative 2. Same thing is alternating. First one is, let's say first term is negative 1. Second term is 2. Third term is negative 4. fourth term is A, but this one is not converged. Alternating value gonna be increasing. So this one is divergent. So what you did here, guys, R is 0 and 1 converge. R is negative 1 and 0 is converge. R equals 0 meaning is that's constant. That's going to be converge. So here's conclusion. R is between negative 1 is converge going to 0. R equal 1 is going to be 1. That's the converge. What we didn't check is right here. R is negative 1. What happened? A1 is 1. A2 is negative 1. A3 is 1. A4 is negative 1. So this one is what? Divergent. Okay? Alternating but not close any number, that's divergent. So limit of geometric sequence is very important, guys. When geometric sequences converge on two different things, R is between the negative 1 and 1, go to 0. R is 1. Then you times 1 each time. The first term doesn't change. First term, second term, third term, that's always the same. That's going to same thing. So that's what you guys remember here, guys. So let's see the geometric sequence here and find the limit. What do you have to check? The if geometric sequence convergence divergent, what you have to check. Here is idea, guys. Here you have to check R. What is common ratio? Okay, these all three sequences geometric sequence. Before you check the limit of geometric sequence, you identify this sequence is geometric or not, but I give the geometric sequence. So let's just start the first one, A. So how you figured it out, the ratio? You write down couple term. First term, when you plug in the 1, negative 1 over 2. Second term, negative 1 over 2 square 1 over 4. Third term is negative 1 over 2 and cube, negative 1 over 8. So what happened? Negative 1 over 2. What happened? Negative 1 over 2. Common ratio is negative 1 over 2. This one is between the 1 and negative 1. So this limit gonna be 0. That's easily you figured it out, the limit of geometric sequence. Let's go to B. A1 is negative 2. A2 gonna be 4. Alternating sequence, right? A3 negative 8. So each time ratio gonna be negative 2. R is less than negative 1. That's gonna be divergent. Let's go to C right here, guys. Oh, here is, I made a mistake. This one is not there, guys. This one, next term is 1 over 64. What is the ratio here, guys? 1, 1/4, 1 over 6, and 1 over 64. So each time you times R is 1 over 4. 1 over 4 is between the negative 1 and 1. So this one is the limit of this sequence going to and 0. So you first thing you have to do, identify geometric sequence, then you're gonna find the ratio, common ratio. Ratio gonna be between negative 1 and 1, that sequence going to 0. Ratio gonna be 1, which meaning is every term of sequence is the same thing. That's going to that first term, otherwise divergent. We have one more theorem to find the limit of sequence, guys. This one is a little abstract. First, I give it two definitions of sequence. So first one is monotonic sequence. Simply monotonic sequence meaning is, guys, here is right there. Sequence is increasing, like increasing function. Sequence increasing, which meaning is A1, A2 is bigger than A1, A3, that's increasing sequence. Another thing is the sequence is decreasing, then A1, A2, A3. A1 is biggest, A2 is A1 is bigger than A2, A2 is bigger than A3. So sequence is going to be increasing or decreasing. We say monotonic. Okay, so I'm gonna give the example here, guys. Example here. So first example, V and I show this sequence gonna be decreasing. So how can show decreasing is? Decreasing meaning is the first term, A1, 1 over 6, A2, 1 over 7, A3, 1 over 8. Guys, right? But denominator 6, 7, 8. Of course, this one is decreasing. 1 over 6 bigger than 1 over 7. 1 over 7 bigger than 1 over 8. So you're going to say this is decreasing. Okay? Let's go another example, guys. How about n squared? That's going to be increasing. Why? A1 is 1 square is 1. A2 gonna be 2 square is 4. A3 gonna be 3 square is 9. So first term is 1, second term is 9. That's gonna be getting bigger and bigger. That's called increasing. Okay? So sequence is increasing or decreasing, we're gonna call monotonic sequence. All right? Next one is another important definition of sequence is bounded. So sequence is bounded above and below, which meaning I'm going to call you sequences AN is right there, or sequence is less than some number, greater than some number. That's what we call bounded. Bounded above, bounded below. Bounded above, bounded below. Below, smallest number gonna be greater than some number, less than some number. That's the bounded sequence. When you can find some number m, small, so some number m, low bound, upper bound, then sequence gonna be bounded sequence, okay? So I'm gonna give the one example here, guys. Example here. First one is 1 of n is bounded. So you're going to pick the upper bound, the lower bound, any number, but all sequence between the two numbers. That's going to bound the sequence. So this one is 1, 1.5, 1/3, 1/4, 1/5. So what are you going to say? This 1 over n, all the greater than 0, all going to be less than or equal to 1. That's what we call 1 over n is bounded because you trap the sequence some two number between the two number. That's gonna be bounded. But the other one, look at this. Here is n is unbounded. So first one, 1, 2, 3, 4, 5. So this one is n is of course greater than 1, but we're gonna find this less than m. We cannot find this number because this sequence is increasing, right? So this one is unbounded. Do you get the idea of bounded, unbounded, right? Sequence is increasing, that's we call keep increasing unbounded, but you put the sequences one, how can I say, one pocket. So lowest, low bound, smallest number, biggest number, then you put the order sequence there, that's gonna be bounded. This is last theorem to find the limit. Sometimes we cannot find the limit of sequence, but this theorem is some idea the sequence has limit or not. Sequence is convergent or divergent. Sometimes we cannot find it, but got the idea sequence has limit and convergence. So if this theorem say right here, guys, what do you have to check? Sequence is bounded or increasing, bounded or increasing, then sequence have limit, sequence is convergent. Bounded meaning is here is L number, guys, right here. Some number, all sequences between the two number, greater than 0, less than m. and sequence is increasing. Its increasing function looks like, or decreasing function, then sequence has a limit. So sometimes we cannot find the pattern of sequence. They give this form of some recursive sequence form, then we can find the limits. Okay, let's have this example, guys. Look at this very carefully. AN is defined recurrence relationship. They not given specific terms, or we cannot find the general term. That's the key idea here. There is no general term, or we don't know the list of number. So that case, only we're gonna find the limit. This sequence has a limit or not. They only give the relation between the an plus 1 and an. So we want to find the limit of this sequence, but we can use the monotonic sequence theorem. If this sequence is monotonic, increasing or decreasing, and bounded by some number, then we're going to say this have a limit. So I'm not going to prove this sequence is increasing or bounded. Then I'm going to show how I'm going to find the limit. So this is a monotonic sequence. Say, you can check it on my note. This sequence is increasing and bounded. They guarantee they converge, which meaning is a limit. And approach the an, gonna be certain number. That's approach the specific number. That's the a. So we're going to find a value right here. What is A going to be? So they exist. So we want to find it. So we're using this one, guys, okay? So limit, take a limit both sides, an plus 1, limit 1.5, an plus 6. So this one is a limit and approach to infinity, 1 over 2 an plus limit and approach to infinity 6. So let's thinking about limit meaning. Limit meaning is end behavior, right? An go to where? A1, A2, A3, A4 keep going, they closed A. So this one is meaning is limit and approach to infinity an plus 1, even n plus 1 going to A. So sequence and behavior is A. It doesn't matter here is right n plus 1. So you have C. This one going to A, okay? A equal, here is 1 over 2 outside, 1 over 2 limit, and approach to an. 6 go to where? First term 6, second is a 6, third is a 6, fourth is a 6. This gonna be approach, of course, that's going to 6, right? So we know that this limit is gonna be A again. This is 1.5 A plus 6, right? Now, what do you have? A equal 1.5 A plus 6, A minus 1.5 A equals 6, 1.5 A equals 6, A should be 12, conclusion is limit, and approach infinity, A n going to 12. So that's you're gonna find this limit, guys, okay? This last example is we use a monotonic sequence theorem. Sequence is monotonic and bounded, then we can find the limit.